Now let's look at the various ventilation systems. We'll look at natural ventilation first. We normally express the ventilation requirements in terms of AVCV, which is the aerodynamic free area. So what is aerodynamic free area, and why do we calculate our result in terms of this? Every ventilator has a geometric area, and that is the measured size of the hole that it produces when it opens. But that geometric area is not 100% efficient, as there is considerable turbulence around the edges. So there is a proportion of the geometric area that is actually useful in terms of providing an effective opening, and that proportion is the aerodynamic free area. The proportion varies from ventilator to ventilator, but the proportion is usually in the range of 0.5 to 0.7 or 50% to 70%. Many ventilators are around 60% efficient, and so a default proportion of 0.6 or 60% is usually assumed when more precise details of the ventilator are not known. The geometric or measured area of the ventilator is designated as AV, and the aerodynamic free area is found by multiplying the geometric area by the coefficient of ventilation, and it is designated as AVCV, which represents the product of the two terms. So why do we generally calculate AVCV and not AV when we work out the required area of ventilation for a reservoir? Well, we don't always know which precise ventilators are going to be chosen to provide the ventilation, so we don't know what precise CV value they will have. What we can work out is the effective area of ventilation required, that is the aerodynamic free area, and then it is up to the building designer to choose the ventilators that best suit his design needs and that also suit the functional needs of effective smoke exhaust. Let's move on to calculate the area of ventilation required in a naturally ventilated atrium. There is one basic formula, and it can be presented in a number of forms. This is the first form. In this equation, AVCV is the aerodynamic free area of ventilation required in each reservoir. M smoke is the mass flow rate of smoke into the smoke layer. Rho naught is the ambient air density in kilograms per cubic metre, usually taken to have a value of 1.2. TL is the average absolute temperature of the smoke layer. T naught is the ambient air temperature in Kelvin. AVCV divided by AICI is the ratio of outlets to inlets. Provided that all reservoirs in the building have the same area of ventilation within them, this ratio is in practice 1 divided by the number of reservoirs minus 1. It's the fire-affected reservoir divided by the rest of the reservoirs. For example, if a warehouse had 4 smoke reservoirs, we would expect in a fire situation that 1 would be affected by smoke, and so smoke would be leaving by the ventilators in that 1 reservoir. We would expect incoming replacement air to enter the building by means of the ventilators in the unaffected reservoirs, of which there are 3. The ratio of AVCV to AICI will therefore become 1/3 if all the reservoirs have the same ventilation area. Going back to our equation, G equals the acceleration due to gravity in meters per second per second. This is taken as 9.81. D is the depth of smoke beneath the centre line of the ventilators. Theta is the temperature rise in the smoke layer above ambient. This formula, as you can see, gives a figure for the aerodynamic free area of ventilation that is required in each reservoir. Now let's do an example using this formula. Let's suppose that we have a warehouse with a design fire size of 4,000 kilowatts and a mass flow rate of smoke of 47 kilograms per second. These results give us a theta value of 85 Kelvin. If we assume an ambient temperature of 15 degrees C or 288 Kelvin, we get a value for the average temperature of the smoke layer of 373 Kelvin. Let's further assume that our warehouse has 4 reservoirs and that each is to have the same area of ventilation within it. Note that if the same items are stored throughout the warehouse, then it is reasonable to assume that the fire will behave the same whichever reservoir it happens to be in. The design height for the base of the smoke layer is 0.5 metres above the highest rack level, which results in a smoke layer with a depth of 3 metres for this building. That is to say, the distance between the base of the smoke layer and the centre line of the ventilators is 3 metres. The base of the smoke layer, remember, is the position the smoke descends to, but not beyond according to the design of the building. With this basic information about the fire and the building, we can use the formula given above to calculate the aerodynamic free area of ventilation required in each reservoir. We have the basic formula here, so let's enter the values of the variables that are appropriate for our building. This gives us AVCV equals 46.7 divided by 1.2. And then inside the brackets, we've got TL replaced with 373. The ratio AVCV over AICI is 1 over 3. T naught is replaced with 288. And on the bottom line of the equation, we've got 2 times 9.81, which is the acceleration due to gravity, times 3, the depth of the smoke, times 85, which is theta, times 288, which is T naught. And the last brackets are all raised to the power 0.5. Evaluating this gives 12.6 square metres of aerodynamic free ventilation in each of the 4 reservoirs. Now let's look at an alternative method for determining the area of ventilation in terms of AVCV. The second option from BR 368 and PD 7974 Part 2 is shown here. This has the same variables and is in fact merely a rearrangement of the previous equation. This equation does not use the ratio AVCV over AICI, but instead uses the direct figure for the area of the replacement air inlets. This equation, therefore, can be used where there is only a single reservoir and where replacement air is being drawn in through specific vents at low level, or where areas of ventilation in each reservoir are different from each other. David's now going to look at an example using this equation.